Hi again, my name is Jan, welcome to another video on this channel. I took a little bit of a summer vacation break and now we're ready to go right back into business on the MinuteMan machine. Digging deeper into our rabbit hole, we're trying to find out if it's possible to 3D print a Benchy in less than a minute. Today's topic is going to be motors. So this is the style of motor we have been using for the entire testing time. It's a NEMA 17. This one is not, but the ones we're using were from LDO, the Speedy Powers. And today we're gonna focus on a slightly bigger version. So that's one of the most powerful NEMA 23 stepper motors I found. I got 4 of them lined up and already put all the accessories on it. And we're trying to find out if it is possible to have enough power and dynamics to follow our G-code in less than a minute. As it turns out with these, I've been doing a lot of simulation and I think that we're running into torque issues here. And that's what we're trying to find out with this guy. Also, we need to conclude today if it is even possible to do with stepper motors. It's basically, when you look at 3D printing, etc., it's an age-old technology and there are certain limitations to what this system is capable of. For 3D printing hobbyists, that is a total viable solution because it is very obtainable, it is dirt cheap and easy to control, and everything in that environment of 3D printing is basically built around stepper motors. But today I want to see if we have to go a different route to do it, and this is the same style or same form factor servo. If we don't manage to get the results we need, it is all interchangeable, so I could give the servo a go and enter a really different kind of realm in terms of motion systems. This video will have a sponsor, more on that later on in the video. So let's play the intro and let's get started on our today's topic. Alright, you saw me filming some kind of an intro. It is like 12 hours later and I got some company here in the company. So this is Julien. This is also the guy that helped me programming the solar robot. And right now he's helping me with some analyzing on the motor situation. So Julien, would you like to explain briefly what is going on here?
So this is a Shady 80XL gravity sensor. Then an ESP32 is reading it out and it sends the data back to our PC, which I have written in Python program for, and this is the plot.
What do we think is the benefit of that? We could use the Clipper internal device for measuring, but we do think this has the benefit of getting more information out of it. And our ultimate goal is to find out what the biggest acceleration on this setup here is and then compare it to the other ones. We wrote some G-code that increases the acceleration by 10k with each move. Right now we're only going to do a move in one axis and maybe later on combine these. I'm just going to hit go and you will see one cycle. The last one should be about 200k and this is the measurements that are coming in on the screen. So basically what we're interested in are these spikes because we set the acceleration to a certain limit. If we do have step losses, we assume that we cannot hold the given acceleration we requested the system to do. But maybe because of some resonances or something, the acceleration that was on the system itself was way higher than that, and yeah, that's basically killing our maximum performance. Right now we're debating over the results of this setup in terms of sample rates and how often we do have to reproduce a measurement or a linear movement to actually be really sure, we'll get you into these measurements sooner or later. It's the next morning. We actually did do testing past 12 o'clock and yeah, I wasn't really wielding the camera at that point too much in the process of finding out the ins and outs of the accelerometer. While the sample rate of these ADXL accelerometers may be fine for slower or mediocre speeds, for this it just doesn't cut it. We have to overlay various numbers of samples to get a really good measurement on that. We concluded that we have to give it another try at a different point in time to actually get test results that are like helping us on this project. And that's what we're going back to at a later point. For now, I bet you just saw it in the video yesterday, but now you can have a look. I built a desk for the machine to get some more space.
What follows is a brief construction montage. We hope you enjoyed this brief construction montage.
And as you can see, these are the two drive units from these two machines. I open up some space here. These make a pretty solid desk stand. And also, these two drive units were bad when I bought these machines. I have no idea what's the problem with those, but those haven't been rated in terms of their internals. If anyone is interested in any of this stuff that's inside here, maybe also write me a mail or a PM on YouTube. Concerning the motor situation, I found the 80% limits of what these motors on this setup are capable in earlier testing. It heavily depends on the square corner velocity and the G-code I ran. Just with single line movement, I was able to go somewhere like 400 to 420 meters per second squared acceleration. In real printing applications like a Benchy G-code, that is going down to somewhere in the neighborhood of 300K. While that being a pretty impressive number, it is far off from what we need to actually print a sub 1 minute Benchy. I concluded we have to go somewhere in the realm of 600K accelerations in order to do that. There will be the point where we go and do the final motor iteration and then fine-tune those guys to work at their absolute limits, but it doesn't make any sense to do that as of right now. We know this setup, and even with a lot of fine-tuning, we won't be able to reach the speed we need. My proposal is, let's put the NEMA 23 motors on there. It will take me a while to get all that sorted out, and just see ballpark area where we end up. Is it 50% slower or is it 50% faster? If we get any kind of these extreme results, I'm kind of happy with, because then we know, okay, we go with the bigger motors, or we even have to try a NEMA 8 or something to go down with the rotor inertia again. I will do that, and then we'll meet back at the bench.
What follows is a brief construction montage. We hope you enjoyed this brief construction montage.
I've set everything up on the machine as far as remodeling it to the NEMA 23 motors goes, but I think it's a great time to actually have a look at what has changed. Let me give you an overview. These are the 4 motors and all the accessories changed. And here I wired in the new stepper motor drivers. So let's start with the obvious things. As I said before, I used the LDO Speedy Power motors. And now we're going to the NEMA 23. So let's talk about the differences. Usually my design approach is always to change just one of the variables in a system to keep track of what's happening and what's going on. But sooner or later, when I realized what we are actually doing here, there are so many things I have to consider, and changing the pulley size, changing different Newton meter settings, changing the motor drivers, etc. That would make up for such a long list that the testing would be basically for days and days. And what my goal for right now is to get an overview. I think this setup will do plenty for that. NEMA 17, NEMA 23. This is like 0.45 Newton meters of holding torque. This has 3 Newton meters of holding torque. It would also take twice the amount of current on it. And when comparing key facts, this has 84 grams of rotor inertia. This has 340 grams of rotor inertia. These two values I just mentioned were like my main point when I was selecting these new drivers. I wanted them to be as strong as possible. That's what you usually get by choosing a very long motor type. But I also wanted to keep the rotor inertia down as possible, because that's basically what defines the dynamic of a motion system. Usually you want to compare the moving mass of your, in my case, bed assembly, and match that to the rotor inertia of one of the motors. So for straight line movement in one axis, you could say that only one motor is actually active in doing the pulling. Because in a rope setup, the additional motor doesn't add any value to the motion. It's just gonna belt on tension in the best scenario. What you usually do is to match these inertias. In my case, this is around 60-70 grams, so I was choosing the LDOs in the first place because they match pretty good. They almost have a 1-to-1 ratio. In mechanical engineering, you say you can choose in a range for like standard dynamic systems from 1-to-1 to 1-to-10. So basically outnumbering the motor inertia to the moving mass inertia by 10. This could also be 700 grams and it will still make up for a pretty reasonable setup. I was going 1-to-1 in the first place, and now we are going like 6-to-1 in the different direction. So basically, we're coming to a point where the bed itself isn't really relevant anymore. If I got like 5 grams or 7 grams or 100 grams, this guy will outnumber him big time. Also, we come to a point where, as I said, this isn't relevant anymore. It is just about what kind of acceleration can the motor itself do. If you compare like rotor inertia to torque, this plays in the same league. And therefore I decided to switch up another variable, and this is the pulley size. So with the previous setup, this was 20 millimeters of diameter, effective diameter of the rope. This has grown to 40 millimeters, pi times the rolling circumference. What this helps me to do is, at least in my calculations, this stepper is being used at a way more reasonable speed as this one. For example, if we're doing 2 meters of linear movement per second, this is somewhere in the neighborhood of 1500 RPMs. It will still do only one rotation to cover all of the whole movement range, but still does the equivalent of 1500 revolutions per minute to achieve this speed. With this motor, however, we are somewhere in the neighborhood of 400 to 500 RPMs on the motor. We are running this at a point in the graph where the motor is still at a very high torque rating. And that wasn't really the case even with the LDO motors keeping their torque up to a very high point. Another variable is the driver's side. These were the old drivers, the TMC 5160 Pro. These are pretty decent drivers. I mean, they max out the maximum amperage any of these boards can do, because just the small little pins can only transfer up to 3 amps. And basically, from what I understand out of the manuals, this is the same chip that's in these badass units. It has way more MOSFETs behind it. I'm powering it with a 60 volt setup as well, and these are able to do like 10 amps on the motor. I installed some proper 3010 fans on here, and according to the numbers on their website, these should run with up to 5 to 6 amps without overheating. I think with this massive of a heatsink, this is a pretty nifty unit. That's basically what I changed up expectations for the upcoming tests. I think these will break. This guy has to be redesigned either way, so let's see what these motors can do. It's actually 3 days later. There is massive stuff going on in the background here, so I just have very little time to eventually play on this machine. When I did the initial setup, I mean, it does work right now, but we had a few like minor issues to solve before we can go for the big test, which will be starting now. So first of all, the old 60 volt unit didn't have the current I need to run these bad boys. I upgraded it to a bigger version. Maybe we'll put another one on top to just wire 2 of these to one power supply to max out what these drivers are capable of. Well, then I designed this top plate to go on our existing non-air bearing to reinforce these pillars where actually the cables are connected to. This is a proper setup of like 85 grams total, so I think for final setups we're only going down in weight. And then last but not least, I discovered something pretty interesting. So as you can see here, I put some screws in here to actually hold the cable in place. When I did the initial tests with these motors, I discovered that there was something wrong, or it just didn't feel right, and I was investigating, and as it turns out, the cables were slipping on the pulley. And that is kind of odd, because I thought I never had that problem on the smaller pulleys before in the NEMA 17 motors. And from a equation standpoint, the diameter of the pulley shouldn't influence that, because the area is being cancelled out of the friction equation. But I did encounter slippage, and I caught it on camera, so I had to deal with it in some way. The quick and dirty solution for right now was to just drill 2 holes in here and put some screws and washers on here that will secure it no matter what. But then it got me thinking, if this was also happening on our NEMA 17 tests. I mean, it surely wasn't obvious that it was happening, but maybe in the higher end motions, this was what caused the motors eventually to lose steps, because if the cable just slips a very tiny bit, all the math that is Clipper doing in the background isn't adding up anymore. If we discover that we have to go back to a NEMA 17 motor, I would do this just to be sure for those smaller pulleys as well. I loaded up some G-code, and we're going to ramp up the accelerations from layer to layer and see where we end up and what this system is capable of. These motors are rated at 4.2 amps. Right now I'm running them at 2.5, but since we're using the 60 volt setup, they are getting quite warm in a very short matter of time. So let's see what 2.5 amps can do, then let it cool down, maybe check 3.5. That is what my setup is capable of right now. If that yields the numbers I'm looking for, then we're going with a very big power supply and active cooling on these motors to see where the true limits are. So before the intro, I said today's video has got a sponsor, and I'm proudly presenting that to be me. So I get asked in the comments all the time what I'm doing here, if this is my main job, and how can I be in such a cool workplace environment. And I want to address that shortly. So I'm a self-employed engineer for over 10 years now, and I'm in this exact location for 6.5 years. What I do on a daily basis isn't a straightforward answer. Usually I get approached with a problem. To have an analogy to this project, the question is 3D printing a Benchy in sub 1 minute even possible? Then we're using science to find out. We have a look at the problem, divide it into each and every little function it has to serve. Using the technology of rapid prototyping allows us to go really quickly into finding small little solutions for all the individual functions. And if we did that and iterated in this field, we can put it all together to a final assembly. I don't really sit in any niche, so I'm working with all the materials, starting from wood to plastics to even milling titanium. I do all the metal work in-house, like CNC milling, CNC lathe work, grinding, welding, basically you name it. Since I'm mostly doing R&D work for industry, it's mostly protected by NDAs, so I can't really post that here on YouTube. The things that actually end up on YouTube are the things I do as my hobby. So basically you can see this giant TIE fighter build. Down there you can see the solar-powered robot. In this area is the stereo speaker system I built out of scrap material. So basically what I'm trying to say, if you got a problem, an idea, or you're searching for a solution and you see that in the supervision of a young guy like me, well, yeah, you can find my website down there in the channel description. You can write me an email or give me a call, and we can talk about what I can do for you. So if you made it that far into this advertisement, thank you very much. Let's get straight back to the MinuteMan project and see if we can run these steppers full blast. We're at a pretty interesting point in this project. You haven't seen that much footage because I was struggling myself to do proper testing. I'm pretty much stuck at basically the same acceleration values we are getting with the NEMA 17 setup. This whole setup doesn't scale with the amperage I put on the motor. So with the NEMA 17s it was like pretty much consistent from 1 to 3 amps, and the possible accelerations were climbing pretty much linearly. In this setup that isn't the case. I don't have the amperage right now to fully load the motors to their rated current. The highest accelerations was done on just 1 amp of current, which is like 1/4 of the rated current. Going up with the amperage like to 3 amps, that was the biggest one I did today, doesn't really help. You can see that the motors get wilder, put a lot of stress into the system, but actually the threshold of where it starts to lose steps is basically the same. The problem is we have like 100 variables in this system. There are springs, there are cables, there's moving mass, there's amperage, there's pulley diameter, there is voltage, there's microsteps. For this kind of unproven setup here, it is pretty hard to dial in all the right numbers. And as I said initially, this should have been about finding out if bigger motors equals better. This is exactly where I didn't want to end up, to be somewhere matched with the previous setup. So I was hoping that one of these setups is like 50% better than the rest, and then I can focus on just fine-tuning one of these. Also, just having all of this set up was like 1 day of work to, I'm trying to figure out what we're gonna do next. I think this setup, as well as the previous one, is capable of doing, let's say, a 2-minute run. I've ran 3.5 minutes today. There is lots of headroom just by fine-tuning parameters. I can confidently say a 2-minute run would be possible. Also, I don't think I have fair grounds of proving or disproving the question, is a sub-minute run on steppers possible? But as of right now, it pretty much points to a no. At least if we're using somewhat off-the-shelf solutions regarding steppers and stepper driver. All the other guys that are running steppers on their modified 3D printers do end up somewhere in the neighborhood of 250 to 300k accelerations on the axes. So maybe we're just running into constraints with the steppers itself. Something about field strength and rotor inertia ratio, something like that. So I don't know, this video is already pretty long. Of course I wanted to end it with some kind of a banger. A dry run that is very close to 1 minute or something, but I don't think I have that on me right now. Maybe if this is the end to the video, I'm gonna close this with what's your opinion on this setup? What parameters could be changed to make it happen on here? Do we have to go all in and like machine rotor inertia away, get the rotor out of the stepper and mill away everything that is not necessarily needed in there? I mean, let me know in the comments. And if we want to make the sub 1 minute benchy on stepper motors possible, if there's any company or you know someone or work in some kind of a strange industry application that would say, hey, yeah, I do have stepper and stepper drivers, etc. that can do all of that, and you want to have it displayed here, we can test that out. So I guess we have to go somewhere in the neighborhood of 500 to 600k accelerations while accelerating 70 grams of moving mass. So that's the task. Hit me up, write me an email if you think you got the hardware to do it. So this is definitely not the end of the stepper journey. At least I want to print something with this setup, go down in our benchmark numbers. And before I say, no, it is not possible to do, we have to do some investigation. The main issue here is you can't see anything of that with your own eyes. I do lack of a proper slow motion camera. It's pretty hard to investigate what's actually going on here. Let's see. Again, there's somewhere a link down to the Discord. There's a very open and active conversation about this topic. And if you want to join in, feel free to. I would appreciate your company. So maybe see you next time or down in the comment section. Bye-bye.